So ordinal numbers are ways of counting. Okay, so they start with the usual counting numbers 0, 1, 2, etc. But then you have other numbers that are bigger than this, like omega, omega plus 1, 2 omega, and so on. And somewhere down the way we have omega 1, which is going to be called the first uncountable ordinal. And this will let us, the value of these is we can go beyond sequences using these things, what is called transfinite induction. And for us the value is, it will show you need to go beyond sequences. That is a space that is not first countable. Okay, so but first, before I get into this, I remark, if you take R with or any uncountable set with cofinite topology, okay, then neighborhoods of any point are excluding finite sets, so this is not first countable. Okay, this is an easy exercise, is not first countable. So before embarking on this, however, this is not even Hausdorff. So when we want to understand how first countability or second countability play a role in being, say, a metric space. So last time we saw that metric space implies first countable. So if you're not first countable, you can't be a metric space. But this is not a metric space for much more elementary reasons. And these ordinals are also important in constructing things like what are called long lines, which are interesting examples. So we'll go with these. So we have these, so that was a digression, but we want to talk about first uncountable ordinal as an example with the order topology. So let us, so to define these, we'll define a linear ordering, linearly ordered set. So far we just have a set S and less than is well ordered if any subset A in S has a minimum. Now this is one of the ways of formulating induction in natural numbers. Okay, so if you want to show a property holds by induction, if you know natural numbers are well ordered, you look at the smallest set of numbers where the property is false, find the smallest one, and then get a contradiction. Okay, so well ordering lets us do induction with natural numbers, and it's a definition that doesn't depend on S being even countable or anything else about S. It makes sense for everything if it's ordered. So given the well ordered set, we'll not define the ordinal numbers in their full generality, but elements of well ordered sets will give us what we need. Okay, so so the following theorem depends on Zon's lemma, and if you're familiar with Zon's lemma, you can see a quick sketch of I'll give a quick sketch of the proof. For those not familiar, I'll have to refer elsewhere. This will be a bit of a digression anyway. So a theorem is that any set can be well ordered. This is very similar in nature to saying any vector space can have a basis. And if you recall, the way in which a vector space has a basis is you find a maximal linearly independent set, okay, by repeatedly extending linearly independent sets and show that this is a basis. So here there is something else similar, namely we consider well orderings of subsets of S, okay, and then we order these themselves, which are ordered by, well, if I have B and a well ordering is less than or equal to A and some less than or equal to sign, so some order on B on A. If B is contained in A and less than or equal to B is a restricts less than or equal to A. So if we have an ordering of B, and then we have an ordering of A, then the ordering, sorry, if I have two elements in B, the order is exactly the order in A. Okay, so it's actually easy to see any restriction is automatically a well ordering, but here we have an ordering on the on the well orderings of subsets of S. Okay, now any chain has a maximal element by taking union. Okay. Again, in this video, assuming that you have seen some proof using Zorn's lemma. So for example, if you have seen the proof that every vector space has a basis, what you show is the union of linearly independent sets is going to be linearly independent, because linear independence depends on finitely many. But a similar thing works here. If I take a whole bunch of sets which all have ordering, so that when a chain is something which is a totally ordered subset, which are, I should emphasize here, this is only a partially ordering. So a chain is a totally ordered subset. So if I take a totally ordered subset, then it's a collection of subsets of S on which we have orderings, and they are all consistent with each other, they restrict. So we take the union of these, and then on that we have an ordering, namely any two elements must be in some set, and hence in some bigger set, and we can, because of the total ordering, and we can use the order from that bigger set. So this is any chain has a maximal element by taking the union. And what do we have beyond this? So we consider well orderings of subsets of S, which are partially ordered by this. Any chain has a maximal element, okay, hence by Zorn's lemma. Oh, sorry, any chain is bounded above. Okay, the union may not be in the chain, it is bounded above. Yeah, so hence by Zorn's lemma, there is a maximal element. And what do you do when there's a maximal element? If this is not a well ordering, so this maximal element has to be well ordering on a subset on T contained in S, and T is not equal to S. So if it's a well ordering on S, we are done. Okay, then pick some element, let's say little s in S minus T, and order with S bigger than everything in T. Again, let me clarify the logic in words. We want to show that any set, let's call it S, can be well ordered. We look at well orderings of subsets of S. There are some, namely you can take single element subsets and you just have a trivial ordering on them, or two elements. Indeed, any finite subset can be well ordered. We know that we can well order even natural numbers. Okay, we look at well orderings of these and order them by saying one is before the other if it's a ordering on a subset which is a restriction. Now what we know is that if we take every chain is bounded above, that is if I have a totally ordered subset of the set of well orderings on subsets of S. Okay, so if I have, that means that I have a collection of well orderings on subsets of S, so that given any two of them, one is bigger than the other. Or they could be equal also, bigger in the weak sense of the other. Okay, if I have a totally ordered such chain, then I take the union of these and see that these give you a consistent well ordering on that. And because this is a consistent well ordering, we are yeah, so that's that. So we have a consistent well ordering on this. So Zorn's lemma tells you there's a maximal element, and in linear basis case you would show maximal element must span, otherwise you take something outside the span. Here you do something similar but simpler. Take a element which is not in the well ordering and just declare it bigger than all the elements. And it's easy to see this is a well ordering, because if I take any set, It either is just this element alone, in which case this is minimal, or it has some elements in T, in which case you take the minimal of those of the set's intersection with T. Okay. So sorry, I have to correct myself. It's well ordered if any non-empty is a subset, of course. Okay. Now the ordinals which we don't need, but I will mention in passing, are defined as in the following way. The well-ordered sets are themselves well-ordered by the restriction, and the ordinals will then be equivalence classes of well-ordered sets with the ordering coming from restriction in an appropriate sense. Okay, so those are ordinal numbers. We won't need this directly for constructing the first uncountable ordinal, though our construction will just be isomorphic and homeomorphic as spaces to the construction actually defining ordinal numbers. Okay, so you take a well ordering on R, okay, and you let omega 1 be the minimal element, such that if you look at the set of all A in R, this is in the well ordering. A is less than or equal to omega 1, the initial segment, or you could take strictly less than. Let's put strictly less than. It makes the difference of only one element. Is should make it at the definition of the set, is uncountable. Okay. Now this must exist. This set is non-empty because R is uncountable. And then we consider the following segment. So you look at 0 and omega 1, closed omega. Okay. So this is all A in R such that A is less than or equal to omega 1. So this is an ordered set. Okay. So a space with the order topology. And exactly the fact that omega 1 is uncountable, the initial segment of omega 1 is uncountable, shows you that this is not first countable. Namely, if it was, then by definition of order topology, when we look at the basis elements of, so I have omega 1 here, I have a basis elements which, given any set, there will be a basis element bigger than that. Okay. And hence you will get countably many sets. So you get a count. So any set here before omega 1, its initial segments, things up to that are countable. And so you'll get a countable union. So if you had a countable basis, you can show the initial segment of omega 1, that is points before omega, are a countable union of countable sets, and hence they would be countable. But we know this initial segment is uncountable, which is a contradiction. So this was a slightly complicated example, but it has all the niceness separation properties, Hausdorff and so on, but it's not first countable.